Welcome to the course Microprocessors and Robotics. This is week 1. So in week 1, I'll be going over an introduction of the course, and this will be considered your first lecture. So typically every week I will be uploading a lecture where I'll go through some PowerPoints and explain the concepts of the class and any assignments that you may have. This week, as part of that course introduction that I talked about, I will be giving you an overview of the syllabus and pointing out a few key items in there. We'll also jump right into the course material talking about what is a microprocessor, what is a microcontroller. This course is called Microprocessors and Robotics, but we also have a very heavy focus, if not more so, on microcontrollers. So we'll learn what each of those are and the difference between them. We'll also take a look at what analog and digital transmissions are. Those come into play when we're talking about microprocessors and microcontrollers and systems of that sort. And lastly, this will be our first look at binary and hexadecimal number systems, which will be focused on heavily for the next couple of weeks. So before I get into the syllabus, I want to take a quick look at the course topics and explain a little bit about the intentions behind this course and what sort of material we'll be covering. This is outlined in the syllabus somewhat, but I think it's easier to go through in bulleted form here. So the first thing we're going to be covering, you just saw a slide ago, we're going to get into the binary and hexadecimal number systems. Typically we use a decimal number system, so we're going to be looking at 2 alternate number systems that are used very heavily in programming. We're also going to be exploring logic gates and how those factor into programming. We'll be looking at microcontroller architecture, so what are the main pieces of a microcontroller, and then we'll spend a couple weeks learning how to program in assembly language, and then we'll spend around 1/3 of our course covering programming in C language. And then at the end of the course, you'll have a final project where you'll program that in C language. After that, we'll be covering some inputs and outputs for microcontrollers, how different components will interface with them. Playing into that is motors. We'll go into a little bit more detail there. We'll also be talking about communication devices, sensors, and then we'll get into robotics a little bit the last couple weeks. So we'll talk about different kinds of robots and some of their applications. Here are the first 2 pages of the course syllabus. I'm not going to go through everything in great detail, but there are a couple of main things I want to touch on. In the top left, you'll see I have a basic course information note. It looks like that little sticky note there. I've provided you with my email and my response policy. So I have what I call a 24-48 hour response policy. What this means is that on a weekday, if you email me on a weekday, I'll respond to you in 24 hours. On a weekend, Saturday or Sunday, I'll respond in 48. So just bear that in mind when you're reviewing your assignments. If you have any questions, try to take a look at those at least 24 hours before they're due, really 48 because they're typically due on Sunday night. That way you allow yourself time for responses to any questions. I also have a recommended textbook for the course, so it's not required. I just recommend it if you feel like you would like some additional learning resources, if you are somebody who enjoys reading to take in the content. Of course, if you feel like you need more assistance, you can certainly ask me. We can review things in the live session every week. But if you're somebody who prefers a textbook for whatever reason, this is the one I recommend. It covers the course content really well. C programming, it doesn't get really in-depth there. That one, there's other Arduino resources that I would recommend. But for the first half of the course, this textbook is really relevant and really helpful. So the best place I've found this is on Amazon. You can rent it for about $35. You don't have to get it there. Again, this is just kind of the most cost-effective place that I've seen it. So I don't care if you get it from Amazon, somewhere else, the university bookstore, if you rent it, you buy it, whatever you want to do. This is just my suggestion. I'm not going to review the description and the learning goals real in depth. We just covered the main portion of those in the previous slide. You're quite capable of reading through these. The learning methods, so every week there will be a lecture. You can expect that, covering the main course concepts. Discussions will occur not necessarily every week or on a set schedule, so not to say every other week, but just as they come up, I will make you aware. You should expect around 8 discussion assignments this semester. Also, a big component of this semester will be your labs and lab reports. So I will give you labs with full instructions, room for your responses for you to fill out, and you'll be expected to complete those. If you run into issues completing your labs, of course, I recommend the internet as a first resource. Try to figure it out yourself. And I say this too because in the real world, right, in your career, maybe you already have a job in engineering or in some other field. When you run into issues, your first reaction should not be to run to your boss. Your first reaction should be to figure it out yourself or to try to figure it out yourself. So this is where I encourage you to look online, see if you can find a solution. I've switched to the Arduino boards largely because there is so much material on these online. So chances are if you run into an issue, somebody else has too, and there's information about it out there. That being said, you can absolutely ask me questions. You can email me, we can set up a meeting time if we need to. I'm more than happy to answer questions. I would much rather answer your questions and help you figure out issues with your lab than for you to submit your lab late or for you to tell me you just couldn't do it. So bear that in mind. Also, your fellow students are a great resource. They may have also run into the same issue and you guys may be able to help each other out a little bit. My late assignment policy, which we'll get to, does apply to your labs as well as your homework. So just note that, and I'll go over that in the next 2 slides here. I do require a couple of lab materials. The first is the Arduino Uno Rev 3 microcontroller. So I recommend purchasing this directly from the manufacturer. You can purchase it elsewhere. I know Amazon has a couple. I would caution you though, if you do not buy it from the manufacturer, really be thorough in inspecting the product, look at the reviews, because there are some counterfeit microcontrollers. They might look like an Uno, they might function mostly like the Arduino Uno, but they're not quite the same, and you could run into issues with them later on. So I think the Uno from Arduino is around $23, $25, something like that, directly from their website. So it's not super expensive. I would just play it safe and purchase it from there. But again, if you purchase it from anywhere else, I just caution you. The second thing you'll need for this course is a selection of resistors, LEDs. You'll need a push button and some jumper wires and a breadboard. So if you have some of this on hand, you can just buy a couple of those pieces to supplement. You don't have to buy a whole kit, but I do have this kit here that I recommend because it is the easiest and most cost-effective way to get all these things if you don't have them already. So again, if you have all of this stuff that I've outlined here, you're good. You probably don't need to buy the kit, but if you don't have any of this, the kit is the quickest and easiest way to get all of these. And I think the kit is like $11 or $12 on Amazon. So again, really affordable, and hopefully you'll continue to use the microcontroller and components long after the course for personal projects. There's a lot you can do with these. Lastly, we have homework. So you have a couple homework assignments. Typically, you'll be assigned homework or a lab every week, not both, but I'll review each homework assignment as it comes up, and these are subject to the late assignment policy. Your biggest assignment for this semester will be your final project. So when we get to that, I will give you a little bit, or a lot more rather, detail on it, but I've outlined the basics here. So we'll start about halfway through to make sure that you have plenty of time to work on this, because I know coordinating things online can be a little bit more difficult. So I've tried to allow us plenty of time to coordinate your project, work out any bugs, get all the components you need. So be thinking about what sort of project you could work on as we're learning these course concepts, how you could tie them in. So as we learn different pieces of programming, different commands, things like that, you'll be expected to tie those into your final project. Um, and you'll work on that as an individual. So in the past, I've had students program a speaker to play a Christmas song. Some of students had lights blinking along with that. Some students had a sensor where you could knock a certain code and it would flash a green or red light depending on if you knocked the correct code or not. So there's lots of projects online, lots of ideas online, lots of inspiration. We'll dig into that a little bit later in the semester, but just be thinking about that we will be getting into projects. And I've outlined here the basics to the projects and what I expect you to be completing. And at the end, you'll also be writing a project report to talk about your steps and your experience with the project and the final outcome. Then on the right side here, I have the approximate schedule for the course. So this is the plan. So if all goes according to plan, this is what we'll be doing for the semester week by week. I'm not going to go through this in super detail, but you'll see the first couple weeks we're just doing number systems, then we're getting into that assembly programming, then the C programming with our Uno board, and then the last couple weeks are more so lectures, preparing for exams, and working on your final project. So if you look at this schedule, this is approximately what you can expect. And then I've also outlined how I do grading for this course near the bottom here. So you'll see on the left side, I have the assignment weights all measured out in this chart. So of course, out of 100%, this is how things are broken down. So you will, 8% of your grade will be research and discussion assignments. So I'll be asking you to make posts or research a certain topic and make a post about it. And that'll be 8% of your grade. The exam 1 and 2 will each be 15% of your grade. Your homework and lab reports, you'll have around 12 of those, and those are the bulk of your grade because that's where you'll really be demonstrating that you've learned the concepts. So 12 of those, that'll be worth 42% of your grade for the semester, and then your final project and report will be worth 20%. On the right side there, you'll see my grading scale. It's pretty straightforward. So anything 0 to 60 is an F, 60 to 70 is a D, 70 to 80 is a C, 80 to 90 is a B, and 90 to 100 is an A. So I don't really mess around with the plus and minus grades. I just do straight letter grades. So rather you have an 81 or an 89 in the course, you're going to get a B. And same thing for all of the other letter grades. So this is the scale, and just keep that in mind as we go through the course and you're looking at your assignment grades. Here's the final page of your syllabus outlining my course policies and university policies. So my policy on late assignments is that I do accept them. However, I do deduct 5% from your grade for each day that it's late. So if you turn in an assignment 7 days late, you get every question correct, you would have got 100% if it was on time. I'm going to multiply that 7 days that it was late times the 5% that I take off for every day. So that's 35% that's going to get deducted from your score. And so in this case, that would leave you with 65% as your actual score. So you can see that's pretty severe if you're turning in your assignments late. And really that's just because it's not fair that you're turning in your assignments late, you've had more time to work on them than your classmates, and that you're able to get away with poor planning. So I strongly discourage that. And again, if you hadn't got a perfect score in this example, if you started out with 50%, then your grade would be almost nothing. So just be mindful of this late assignment policy. This applies to lab, homework discussions, essentially any assignments. The only thing it does not apply to is your exams. So exam 1 and 2, the late assignment policy does not apply. Your exams will be either submitted on time or you will not be allowed to take them. Also, the university has some registration and withdrawal deadlines that I'll cover quickly. So if you are listening to this, you're of course signed up for this course, but this information might be valuable if you're thinking about registering for other courses. So you can register for courses up until September 2nd this year. And you can withdraw from this course without receiving the withdrawal grade of a W up until September 9th. If you withdraw between September 9th and November 4th, you will have that grade of W assigned and it will show up on your transcript. So just something to bear in mind. Also, I have the university policy here for students with disabilities. They are required to be provided with reasonable accommodations. And so I'm more than happy to work with you. Anyone who has a disability will tailor the course, the approach to work with that, but just follow the university policy here and you'll speak to Lori Donnelly through the student accessibility services first, and then you, Lori, and myself will work out a plan. Lastly, but not least, is the cheating and plagiarism policy. So this is not only my policy, but it is the university policy. So we do not tolerate any academic dishonesty, cheating, or plagiarism at all. So if you are getting information from other sources in this course, if you are using their ideas, their quotes, you need to make sure that you are citing them appropriately. You cannot claim other ideas as your own, is essentially what it boils down to. So I am not real particular on how you cite sources. I don't care if you use APA, MLA, or anything like that. I don't care if you just put in a web link. As long as you are properly citing your sources in some manner and you're not trying to pass somebody's work off. So throughout this course, you'll see the terms microprocessor and microcontroller thrown around a lot. So I want to take a look at these so we can differentiate between the two. Microprocessors only have a CPU, so they are just part of a system. They can be very powerful and very fast, but they don't perform any specific task. So they're doing all these calculations and they're doing all this thinking. They're essentially the brain of the computer, but they do need additional support to function. Whereas a microcontroller may contain a microprocessor, but it also contains other components within it that essentially make it a mini computer. Because it's a mini computer, it can't do anything. So a microprocessor can do just about anything. It has an unspecified application. A microcontroller has to have a specific application that it does. Just like if a dishwasher, they specifically are washing dishes, right? They're not running around a whole restaurant. They have one job that they're performing. So that's typically where we would use a microcontroller. It's kind of a small contained system that could be a standalone unit for one specific task or a few specific tasks. Here we have a couple different examples of both microprocessors and microcontrollers. On the left, these pictures are not microprocessors themselves, but they represent tasks that a microprocessor helps perform. So we have things like Photoshop, Excel, the internet. These things are helped or they're using a microprocessor to help them complete tasks. So a lot of these things, there are no expected inputs or outputs. There could be a huge variety, so a microprocessor is needed to handle those. Whereas for the items on the right, there are a very small set or a manageable set of expected inputs and outputs and computations. So a microcontroller can handle those. For example, the toy robotic dog we have, the microcontroller is probably expecting an input in the form of light or sound, and it's going to give an output probably as some sort of sound or movement. So it's performing a very limited application, which means we can use a microcontroller. So now I want to take a look at a couple examples and I want us to determine if they are using microprocessors or microcontrollers. So typically when we're doing this as an in-class activity, I would ask the class to raise their hand if they think an item represents a microprocessor or if it's using a microcontroller. As we're doing this in an online lecture format, the best way for you to do this, I would recommend pausing each slide before continuing and mentally deciding if you think the item is using a microprocessor or a microcontroller. So this first item here is a dishwasher. It is using a microcontroller. Again, a very set amount of inputs, so it's expecting one of the button presses in the front, and in response it will perform some sort of dishwashing activity. So this microcontroller is performing a specific application. This next item we have here is a laptop. So take a second and decide if you think this is using a microprocessor or a microcontroller. This laptop is using a microprocessor in conjunction with many other components. It is performing a lot of different functions, no one specific application. So a microcontroller would not be able to handle everything going on with this laptop. We would need a microprocessor for this. Okay, and here we have some smart devices, smart watches, Fitbits, things like that. These are using microcontrollers. So again, they're looking for specific inputs and they're performing specific outputs, right? They're doing very specific tasks. They're probably anticipating vibrations from the steps that you're taking or your heartbeat, things like that, and they have a very set output that they're displaying on the screens. So a microcontroller is what is being used for these devices. Next, we have some toy RC cars. So these are using a microcontroller. So again, they're expecting set inputs. So they're expecting an input from the controller, and the output is going to be the car's acceleration, deceleration, or the turning of the wheels. So a very specific application is being performed, very specific tasks are being performed. So we are using a microcontroller for these. And lastly, we have a tablet. So this tablet is using a microprocessor to function. So similar to the laptop, it's performing a lot of different tasks, too many for a small microcontroller to handle. So this laptop, or this tablet, I'm sorry, needs a microprocessor to handle all of those functions. We've been talking about microprocessors and microcontrollers a lot now, but you might be wondering what on earth do these look like? So to help provide a visual, because I think that's always helpful, especially for those visual learners, right? Above here I have a couple different examples of microprocessors. The middle is an especially good example. You can see how it does not operate on its own, but it's integrated as part of a circuit. And here we have some examples of various microcontrollers. These microcontrollers are very commonly used amongst hobbyists, so this might not necessarily be what you would find inside of, for example, like the toy robotic dog, but these microcontrollers are made to be easily used for the hobbyist or for anyone at home programming, or even in a professional environment when we're developing new codes or new programs for things. These are commonly used in that developmental process. So on the left, you'll notice there is a launch pad. This is the type of board that we will be using this semester, but all three of these are very similar. So you can see on these boards, they have different pins where we can connect inputs and outputs, some push buttons, the power, and you might even notice there is a little CPU or microprocessor within these microcontroller boards. So these are all a self-contained unit. Now that we've established what microprocessors and microcontrollers are a little bit, I want to jump into signal and system types. And we're going to talk about digital and analog values. The reason why won't be evident immediately, but we'll see in just a second why this is so relevant to this course. So a digital value is a discrete value. So it's a specific amount, a very specific amount. So for example, everyone who looks at this clock on the left should be able to read that as 1428 or 1428. Those numbers are not left up to interpretation. Whereas on the right, we have analog values. So you're kind of eyeballing where they are in between. Even if you had a very tiny scale, for example, your speedometer would still be somewhere within that scale, right? You would never perfectly be going exactly 80 miles an hour. So when we're talking about an analog system, we're looking at infinitesimal values there. So along with digital and analog outputs that we just saw, there are digital and analog signals. So the top wave example, the square wave, is an example of a digital output signal. So we can see our signal is either a 1 or a 0. It's nowhere in between, right? It's one of those discrete values. It's high or it is low. Whereas on the bottom, we have an analog output signal. And for example, this first wave crest here is up for interpretation, right? We could put a very tiny scale on this graph. We could approximate this is 0.8 or 0.87. We could, go out several decimal places, but it would still not be a perfect reflection of this analog signal. It is always going to be, it's not a discrete value. So this here is where the analog and digital values tie in, especially the digital values or the digital signals. That's what we're focusing on. So in the previous slide, we saw the digital signal was discrete. It was either high or low is the terminology that I used. So we can use this digital signal in our data transmission. So we're looking for high or low. That's something that the computer, the CPU, the microprocessor, they can recognize high and low values. Either something is there or it is not. So we use bits to represent these high and low values. That is short for a binary digit. And a binary digit has a single value of either 0 or 1, high or low. And that is the smallest unit of data that is on a computer. So we do something that's called digital abstraction. And what this means is that we let these high and low bit values, these 0 and 1 numbers, they're representing specific values outside of themselves. So a sequence of zeros and ones is not just zeros and ones, it is representing something else. It could be an image, it could be a string of text, it could be a lot of things. We're using these high and low values to communicate data in our computer systems. And talking about ones and zeros, high and low signal values, that leads us into discussing the binary number system. So what we're traditionally used to is what's called the decimal number system. It's in base 10. So we use digits 0 through 9, right? Every slot or every number place value holds the digit, a digit 0 to 9. And when we run out, we start again. So that's traditionally the number system that we're used to, but in this course we are going to also be taking a look at the binary number system. So it is in base 2, and that means that we're only using 2 different digits in each position. So that gives us the choice between a 1 and a 0, or again, a high and a low value. So binary numbers are very useful for data transmission. To help us further explain the difference between decimal and binary number systems, this picture, this is actually from your textbook, figure 1.4. This is a representation of the decimal number system. So we know that the number 9,742 actually represents 9 times 10 to the 3, which is 1,000, right? So 9 times 1,000, 9,000. 7 times 10 to the 2, which is 700. So 700, 4 times 10 to the 1, which is just 10. So that's 40. This 4 over here, let me get my little pen. This 4 over here is representing 40 units, and this 2 is representing 10 to the 0, which is just 1. So 2 times 1 is 2. So we understand that this number 9742 is actually representing 9,742. Now when we take a look at the binary system, it's the exact same concept, just the place values are a little bit different. So instead of tens to the different powers, we have here 2 to the 0, 2 to the 1, 2 squared. So instead of 10, we're not working in base 10, remember, binary is base 2. So we're working in 2s. So what this means, 2 to the 0 is a 1, 2 to the 1 is a 2, 2 to the 2 is a 4. So these are the new place values. So this number over here, 10110, is not 10,110. It is actually the binary number 22. And I think these little tables help to illustrate that concept a little bit more. On the top here, we have the base 10 system. So these are the place values for each place. And on the bottom here, we have the binary system table. So these are different place values from what we're used to seeing. So just another quick example, if we have the number 142, we understand that to mean 2 times 1 is 2, 4 times 10 would be 40. We'll put our 2 in up here, and then we have 1 times 100, right? So we understand this place value to be 100 times whatever is there. So when we add these all up, we end up with 142. Now, if I put the number 142, or rather 142, down in our binary place system, what this actually means now is 2 times 1 would be 2, and now we have 4 times this place value of 2, which would be 8. And then we have 1 times a place value of 4, which would be 4. So when I add these all up, I actually end up with the number 14. Right? That's what I would end up with for these place values in the binary system. Now, it's important to note when you're using the binary system, you can't actually use 4s or a 2, right? In a binary system, we are limited to 1s and 0s before we run out. But I just wanted to do this example to illustrate the difference in place values with the binary system versus the decimal system. Here's just a little table that shows you the binary equivalents to the decimal numbers that we're used to seeing. So later on in these slides, you'll see how to go back and forth between decimal and binary, but this is just a quick comparison. So for example, the number 8 in decimal actually looks like what is 1,000. But this on the right here is the number 8 in binary when we use a base 2. So when we're limited to just 1s and 0s, these numbers look a lot bigger because we can only count up to 1 before we have to go to the next column. A couple important things to note about the binary system is that typically numbers are written in nibbles and bytes. So those are weird words, I know, so let's break those down a little bit. So a nibble is just a group of 4 bits, right? So a bit is the smallest unit. It's either a 1 or a 0. And a nibble is just a collection of 4 of these. And typically when we are using binary numbers, we will group numbers together in groups of 4, or we'll group them together in nibbles. A byte is a group of 8 bits. This is typically the number that would get processed at a time. So you're processing a byte at a time. And a byte consists of 2 nibbles together right here. So if you were writing out a really long binary number, you would have a small space in between the nibbles and a little bit of a bigger space in between your bytes, your groups of 8 bits. And just like in the decimal number system, any digit that is on the left is going to be the most significant. And any number that is on the right is going to be the least significant number, right? We know over here, this only represents 1. That's not very significant. But moving on, over here in this column, this is actually representing the place value of 8. So this bit is more significant because it is further to the left. In addition to binary, there is one more number system that we're going to be looking at in this week. That is the hexadecimal number system. So as a quick reminder, a binary system uses a base 2. We only have 2 different digits before we start over, right? So we just have 1 and 0. The decimal system is a base 10. We have 10 different digits to use for that, 0 through 9. And hexadecimal is using base 16. So we can represent the digits 0 to 15 in one slot. But you might be wondering, how do we do that when we get above 9, right? We can't just squish 2 digits into one spot. It doesn't work that way. So what we do when we get past 9 in the hexadecimal system is we use letters. And you'll see a table in just a second that shows you what letters correspond to which numbers in the hexadecimal system. Before we get to the letters in the hexadecimal system, I wanted to show you a quick comparison of all of the different number systems we've talked about. So on top is the hexadecimal number system and its place values. So if something is in this third place value right here, it is representing 256. That is that place value right there. This below it is just our typical decimal system, right? Anything in the third column we know is representing that number times 100. And on the bottom we have our binary system. So anything in the third column is representing that number times 4. So this is a good look at all the different bases and place values of these number systems. We saw the place value breakdown before of the decimal and binary system, so now we're going to take a look at the place value breakdown of the hexadecimal number system. And this number may look kind of funny to you right now, 2ED, but that'll make sense shortly here. So what we're seeing is that we're just using a different base, right? So 16 to the power of 0, 16 to the power of 1, and so on. And whatever number or letter is in that place value, we are multiplying it by that inherent place value, right? So instead of ones, tens, 100s columns, up here we see we have ones, 16s, and 256 columns. And just like before, I've included a table that compares these systems for you. And here's where we see the letters come into play for the hexadecimal system. So after the decimal number 9, we have 10, and we run out of digits to represent that. So what we do is we use the letter A to represent 10 in the hexadecimal system. And this continues onward. 15 is the highest number, right? We have 16 different things that we can represent in the hexadecimal system. So we go 0 to 15, and we represent 15 with the letter F in hexadecimal. So if you always, or if you happen to forget which letters correspond to which numbers, just remember it starts at A and 10. So 9, you can always think in your head, okay, 10 is A, that means 11 is B, 12 is C, and so on. You can kind of count that out in your head to figure out the corresponding letter to the decimal number. Now that we've familiarized ourselves with these different number systems a little bit, we're going to take a look at converting between number systems. So you might see the binary number 1010001, but what does that mean? So to help add meaning to these different number systems, we're going to look at converting them back and forth. So we're going to look at decimal to binary, vice versa, decimal to hexadecimal, vice versa, and we're also going to look at the conversions between binary and hexadecimal. So we're about to jump into a lot of different conversion examples here. And before we do that, I just want to let you know if you feel that you need more examples or if you're still confused about the conversion process, please feel free to email me, or YouTube also has a lot of great resources that can walk you through the conversion process with some different numbers if you feel like you still need some more practice. So let's jump into it. Here is a binary number 0010. Okay, great, but what does that mean in decimal? So let's take a look at that. So I have this little reminder of our place values here. And again, just like we do in the decimal system, each number is multiplied by the place value. So all the way on the right, we are going to start out with number 1. I'm going to multiply that by the place value of 1. Right? So 1 times 1 is just going to be 1. And then the second column, the place value is 2. So we're going to multiply 1 by 2. And that's all we have. So the next step we are going to do is to add these up, just as we would for the decimal system. This is probably very similar to what you learned in maybe first or second grade about the decimal system. We're just applying this to a different base. So when we add these numbers together, we end up with 3. So the number 0011 in binary is actually equal to the decimal number 3. And here is our second example of converting a binary number to a decimal number. So this time we're starting out with 1010. And again, I'm going to pull up these place values for us as a quick reminder of these place values. I would recommend writing these out the first time you are doing conversions or when you first start doing them. As you get more proficient, you might be able to remember in your head that this third place value is equal to 4, but I think it's always helpful to write these out. So starting in the first column, we're going to do 0 times 1. That's going to be 0, of course, right? And moving on, we're going to do 1 times 2, which is going to be 2, of course. 0 times 4 is nothing, and 1 times 8 will be 8. So here are the values that you should have ended up with multiplying down the values times the place values. And then the last step is simply to add these up. So we're essentially looking at 8 plus 2, which is going to be equal to 10. So this binary number 1010 is equal to the decimal number 10. Okay, I have one more example of converting binary to decimal, and this is a lot larger number this time. So we are looking at a whole byte of information. Before we were just doing 4 bits or nibble at a time, right? So now we're going to move on to a whole byte of information. But it's still the exact same process. So again, I'm just going to pull up these place values here for us. And we see as we continue to the left, we don't start over with the place value, but it just keeps getting bigger, right? So all these place values is 2 to some power. That keeps increasing. And I've just written out the results of those. For example, 2 to the 4th power is 16. So I've put these here as our reference. Okay, so I'm going to pop these numbers up on the screen for us, but we'll walk through them real quick. 0 times 1 is 0. That's what we've got down here all the way on the right. And then next we're going to look at this 1, and the place value of that is 2, right? So looking down, 1 times 2 is going to be equal to 2. And then these next 3 columns have a value of 0. So just like in any other number system, if you see a 0, it's just representing 0. All right, now we're on this column, third to the left over here, and that's going to be a place value of 2 to the 5, right? So 32. So 1 times 32 is, of course, going to be 32. The binary system is pretty easy to multiply. It at least makes it easy for us. Moving on to this next one, this place value is worth 64. So we're going to write 64 in here. And again, it's just 2 to the power of 6 because we are 6 places over. So 2 to the power of 6 is 64. That is this place value. And the last one is going to be 1 times 2 to the 7, which is going to be 128. So now we have the actual value of all these place values down here at the bottom. The only thing left to do is to add these up. And we end up with the decimal number of 226 for this binary number at the top. This is the decimal equivalent. So hopefully now you have a good understanding of how to convert binary numbers to their decimal equivalents, but now we need to be able to go the other way. So if we start out with a decimal number, how do we find out the binary number? So we're starting out with the decimal number 13 at the top here. And on the bottom, I've just included the binary place values, again, for your reference, because this will make things a little bit easier. So this is a really simple process. First, we start out, binary is base 2, remember? So all we're going to do is divide 13 by 2. And we're not going to put our answer in decimals, right? So if you put in 13 divided by 2 on a calculator, you would probably end up with 6.5, or you would end up with 6.5. But the way we want to write that is it's going to be 6, and then we're going to have 1 left over. So if you're confused or you don't remember remainders very well, because they're typically not used, numbers are usually written in decimal form. So the thing to do would be to type in 13 divided by 2 on your calculator. You would get 6.5. So you would want to write down the 6, and then you would want to say, okay, 6 times 2 would be 12, right? And then 13 minus 12 would be 1. So that's how you would get your remainder of 1 put in here. Just a quick little reminder on how remainders work. So we'd want to take this remainder of 1 and put it in our rightmost column, right there. Okay, so now we have our 6, right? We still have 6 left, so we're going to take this down and we're just going to divide by 2 again. So this one is pretty simple. 6 divided by 2 is 3 with a remainder of 0. And we're just going to remove that. We're going to move that remainder of 0 down here to the next place value. So all we're doing in this conversion process, we're just repeatedly dividing by 2 and you're going to move the remainders down and fill in your binary number right to left. So now we have our 3 left. We're going to divide 3 by 2, and that's going to be equal to 1. 2 goes into 3 one time, and we have 1 left. So you guessed it, we're going to move this 1 over into our next column of our binary number. All right, and we still have 1 left. So we're going to do 1 divided by 2, that equals 0, right? 2 doesn't go into 1 at all. So it's going to be 0 with a remainder of 1. And that 1 is going to go in this last column here. So once you end up with 0 as your answer, that's when you can stop dividing. And then that's when you'll move all of your remainders down here to build your binary number. So the decimal number 13 is equal to the binary number 1101. Now we're going to go through the exact same conversion process, just with a little bit bigger decimal number. So this time we're starting out with the decimal number 115. And just like last time, the first thing to do is to divide this by 2. So 115 divided by 2, again, don't forget, use those remainders, no decimals. 115 divided by 2 is 57 with a remainder of 1. So we're going to move that remainder of 1 down here all the way on the right. And make sure that you're moving these remainders starting on the right and working right to left. If you go the other way, that's not going to work. Okay, so now we're going to take our 57 and divide that by 2. That's going to be 28 with a remainder of 1. Again, we're just going to move that down. All right, there's our next one filled in. 28 divided by 2, 14 with a remainder of 0. Moving that down to the next place, 0. And you don't have to fill this binary number in as you go along. You could do all the division first, and then you could write all your numbers out starting from the top. Whichever is preferable. It doesn't really matter. I'm just filling these in as I go. Okay, now we're going to have 14 divided by 2. That's going to be 7 with a remainder of 0. So that's going to go down here. Okay, let me get rid of some of these lines. All right, so now we have 7 divided by 2, and that's going to be 3 with a remainder of 1. So we're going to want to move that down here. And next we're going to have 3 divided by 2, which is 1 with a remainder of 1. So we are going to move that 1 down here, of course. And we still have this 1 left, so we still need to divide again. So 1 divided by 2 is 0, and we have a remainder of 1. And of course, when we end up with this 0 right here, we know we can't divide any further. So this is our complete number. And this is right here, this extra 0 that we're adding is just completing the byte. So this is giving us a full byte of information, 8 bits. Okay, so we've taken a look at the binary to decimal and decimal to binary. Now we're going to look at hexadecimal. So we're going to start out with the hexadecimal number 3F. And this might seem like a weird number to you if you're not used to seeing the letters yet, but just remember F represents the decimal value of 15. So I'm going to pull up these place values again for us. We're just going to multiply down. So whenever you're converting any number to a decimal, just remember you're multiplying whatever the digit is by the place value. So we're going to start with F, which don't forget is worth 15. So 15 times this place value of 1 is just going to be 15. And then next we have 3 times this place value of 16. So 3 times 16 is going to be 48. So when we pull these up now, all we're doing is adding up all of our values together. So 48 plus 15 is equal to 63. So the hexadecimal number 3F is equal to 63 in decimal. And just a quick reminder, this is not unlike, again, what you've probably learned in 1st or 2nd grade, but we're automatically doing this when we're using the decimal number system, right? So if you see the number 142, you automatically recognize that this is 2 times 1 is 2. This second place right here is the tens place, is what you might have called it. So that's actually worth 40. We know that 4 is representing 40, and then we know this 1 in the 3rd column is representing 100. So we know that when we add these together, it's going to equal 142, and that's an automatic recognition for the decimal system. That's what we've all grown up with, right? So when we're using hexadecimal and binary systems, it's just getting used to what those different place values mean. So when we're converting to the decimal system, which is what we know and recognize, all you're going to want to do is fill in these place values as kind of a reminder, and then you're just going to multiply down, just like we do with the decimal system. We're just multiplying down. Except instead of ones, tens, and hundreds, here we have 1, 16, and 256. All right, let me get rid of this, and we will go over another hexadecimal conversion example. So now we have the hexadecimal number A5. So again, I'm bringing up these place values, writing them out for us. So we have 5 times the place value of 1, which of course is just going to be 5. And then we have this next digit is an A, which represents 10. So we have 10 times the place value of 16, which is going to be 160. So we have 160 plus 5. That's going to give us 165. So the hexadecimal number A5 is equal to the decimal number 165. After those two examples, we're going to move on to a little bit more complex conversion. So here we have a little bit larger hexadecimal number, 12FC. I'm going to bring up these place values again for us. And all we're going to do is multiply downwards. So C, don't forget, is the place value of 12. So 12 times 1 is just going to be 12 down here. Then we're going to do F, right? So F is worth 15. So 15 times 16 is going to be 240. Next we have 2 multiplied by a place value of 256, and that's going to be 512. And then we have 1 multiplied by a place value of 16 to the 3, or 4096, which is down here. So when we add all of these numbers up at the bottom, we end up with 4,860. And this number is the decimal equivalent of the hexadecimal number 12FC. So we've converted hexadecimal to a decimal number. How do we go the other way now? If we start with the decimal number of 37, how do we find out the hexadecimal equivalent? So just like the binary system, we're going to start by dividing the number by the base, right? So we divided by 2 when we were working with binary because it is a base 2. When we're using the hexadecimal system or converting to the hexadecimal system, we're going to use 16 because this is base 16. And again, don't forget we are going to use these remainders. So no 2.6573 whatever. We're going to make sure we write that as a remainder. So we're going to start out 37 divided by 16 is equal to 2, with a remainder of 5. So we're going to write that 5 down in the rightmost place value. So we couldn't do this with binary, right? Binary, we can only use ones and zeros, but hexadecimal, we can go all the way up to 15 or the letter F. So 5 is a perfectly valid number here. All right, now we have the number 2 left, so we're going to divide 2 by 16. Of course, 16 can't go into 2, so that is going to be 0 with a remainder of 2, which we're going to write down here. So the decimal number 37, we make a little note here, this is in base 10, is equal to the number 25 in base 16, our hexadecimal. So this figure here illustrates why it's so important to know which base you're working in. Because if you don't, this 25 could be a decimal number or it can be a hexadecimal number, and they mean very different things. So now we'll do another conversion with a much bigger decimal number. We'll convert the number 15,455 decimal into its hexadecimal equivalent. So of course the first thing we're going to do is divide it by 16, and we end up with 965 with a remainder of 15. But don't forget, 15 is not a valid number in hexadecimal. It is actually going to be F. So looking over at our chart on the right, F is the equivalent of 15, so that's what we're going to write here. Okay, so now we're going to do 965 divided by 16, and that's going to be equal to 60 with a remainder of 5. So we're going to put our remainder of 5 down here. That's a valid hexadecimal number. Okay, 60 now, we're going to divide by 16 again. 3 remainder of 2, or I'm sorry, remainder of 12. 12 is not a valid hexadecimal number, so let's look at our chart over here on the right, and we see that 12 is equal to the hexadecimal letter C. So we're going to make sure that we're writing a C down here. Okay, 3 divided by 16, we've finally got our 0, so we know this is the last time. This is our stop. And we're going to put this last number, this 3, into the next place value. So just to show you what we're doing, again, this is 3 times this place value of 16 to the 3. So 3 times 4,096 plus C, which is 12, times the place value of 256 plus 5 times the place value of 16 plus F, or 15, times the place value of 1. We have 2 more conversions to take a look at now, and that's between binary and hexadecimal. And you might be wondering, why do we need to know how to convert between these 2 numbers, right? Decimal is useful because it's an easily recognizable number. It's what we're all familiar with. But why would we need to go between binary and hexadecimal number systems? Well, hexadecimal works really well in conjunction with binary because binary, I'll show you here. So here in this nibble, we fill this binary number up with all ones, pull in our place values, their equivalents, we add these all together. So this binary number 1111 is equal to the hexadecimal number, or the number, 15, right? So this group of 4 bits here is equal to 15, which is the hexadecimal number F. So instead of representing 15 with 4 places, we can just represent it with 1. So that's why hexadecimal works really well. Again, remember that the computer can only read a high or a low. That's why we use binary. But as an intermediate number system, hexadecimal is great because it's a lot easier to use. It takes up less space, so it's faster, and you're less likely to make errors. So now we're going to take a look at converting binary to hexadecimal first, and here I have a very large binary number in front of us. So I'm going to pull up a reminder of these places. Now, typically when we do a binary conversion, we would go 2 to the first power, right, which would be 1, 2 to the second power, 2, third power, 4, fourth power, 8, and then we would go 2 to the fifth power, right? Which would be 16. But when we're doing a binary to hexadecimal conversion, we start over again every nibble of information. And again, this is because 4 digits in binary is equal to 1 hexadecimal. So don't forget, when you're doing a binary to hexadecimal conversion, you're starting over every 4 bits. So this is why we have 8421 place values written under each of these nibbles. Okay, so looking at this first one on the right, we see all we have is a 1 in the 2 place value. So 1 times 2 is just going to be 2. We're kind of doing a decimal conversion as an intermediate here. So moving on to this next number, 1111. When we add up all these place values, that gives us the decimal number of 15. This next one, we have 1 times 1 and 1 times 4. So adding those together gives us 5, and then we have 1 times 4 and 1 times 8. So that gives us the decimal number of 12. So now we have these decimal intermediates. We're going to convert these to hexadecimal. So 2 in decimal just equals 2 in decimal. 15, remember, we have to write as the letter F. 5 can be written as 5, and 12 has to be written as the letter C. So this is the full conversion. We've taken this binary number at the top, this very long 16-digit number, and we've turned it into only a 4-digit hexadecimal number. So I'm not going to read this binary number up here, but this binary number is equal to the hexadecimal number C5F2. And as you can see, that's a much shorter way of writing that. So it's a similar process to our binary decimal conversion. Again, we're just starting over every nibble with the place values. So you just have to recognize the decimal equivalent of each nibble of data, each 4 bits, and if it's over 9, just remember the hexadecimal letter. Okay, so let's go the other way. If we start out with a hexadecimal number of B4C7, this works in a similar fashion. So what we're going to do is write down the decimal equivalents. We're working backwards a little bit this time from the last conversion we did. So 7 is just 7, C is 12, 4 is 4, and B is going to be 11. Okay, so we have kind of our intermediate numbers. Now I'm going to pull up the place values again for binary, just as a reminder. And again, they're restarting every nibble of data. And we're going to put a little bit more thought into this. So starting on the right, we have the number 7. So you're going to look at what combination of numbers down here is equal to 7. So that's going to be a 4, a 2, and a 1. We're going to need all of these. So this is going to be how we write this binary number down here, 0, 1, 1, 1. So this is representing 1 times 1, 1 times 2, plus 1 times 4, which would be 7. Okay, so moving on to the next number, 12. What combination of numbers do we need down here to represent 12? Well, we need an 8 and a 4. So this is going to be 1, 1, 0, 0. And again, this binary number just represents 1 times 8 plus 1 times 4. And of course, these zeros multiply, don't add anything. So this is a couple different conversions essentially that we're doing here, but it's kept real simple because we're just working with 4 digits at a time. So moving on to the next one, we have a 4. This is really simple to write as a binary number, right? We're just doing 4 times 1. That's all it takes. So 0, 1, 0, 0 is the binary number for 4. And then moving on again, we have 11. So this one might take a little bit more thought. We need an 8, a 2, and a 1. So 8 plus 2 plus 1 is equal to 11. And that's where we get our binary number 1011. And here are your week 1 assignments. The first is not required, it's just recommended if you have the textbook. So I give you the corresponding chapter and pages that correlate to the course content that I just discussed this week. So if you want more material on that, here's where you want to look. The second assignment is your live session time survey. So every week I will be having a live session for about an hour where if you have questions on the course material or if we get into labs, you're struggling with a lab, this is the ideal time to show up and ask questions, get clarification, and have that discussion. So instead of just me picking an arbitrary time and hoping it works for all of you or most of you, I'm asking for your input. So this is essentially just a survey where I ask you what is your availability for these live sessions, and you'll let me know. So on Tuesdays, you would say I'm available from 5 to 7. On Saturdays from 2 to 7 or 2 to 5. So you're just going to go through and check what your availability is, and then whatever hour or hours cross with the most students, that's when I'll set up those session times. So the intent there is to just make them accessible to as many people as possible. I'll go into more detail once I post these, but you are not required to attend the live sessions. They are just there in case you need some more feedback or have questions about the course. Your next assignment this week is homework 1.0. This is posted. It's pretty straightforward if you just go through the questions, and that is due Sunday evening. Your fourth assignment is a discussion post, so pretty light for your week 1 information. I ask that you tell us a little bit about yourself, about your background, and then I have a question that pertains to this course and robotics. So just go through, answer those questions. Your initial post answering all of those questions is due Wednesday on September 2nd. And then I also ask that you make 2 follow-up posts to others by Sunday the 6th. So those are your assignments for this week.